Okay, so let us begin. So guys, in the last class, we were talking about JFET, right? Field effect transistors. We started the very basic discussions about this device. So let me just share my screen with you guys. I guess it's visible, right?
Yes, ma'am.
Yes, ma'am.
Okay.
Yeah.
Okay.
Yes, ma'am.
Okay. So just for a quick recap of whatever we did in the last class. So we were talking about field effect transistors, and the first thing we learned in the last class was the effect called field effect. So what we learned is that field effect is basically something when you modulate the properties of a current flow path by applying a voltage. So suppose a current is flowing in one path and you apply a voltage perpendicular to it, usually perpendicular to it, and you change some properties like conductance, resistance of that particular path. So we call that field effect. So all these transistors that we are learning in this particular module about are all working on this principle of field effect. And then we just learned about the basic structure of the simplest member of this family, that is junction field effect transistor, JFET, right? So in short, we are calling it JFET. The full name is junction field effect transistor. So this was kind of a structure. A replica of this structure you can also consider, where that will be a p-channel FET. So usually we have three semiconductors together sitting side by side, where you have one material of one particular n-type or p-type material sandwiched between two segments of the other kind. So here I have an n-channel FET, where you have an n type of semiconductor sandwiched between two p-type sides. So we take out some terminals out of it. In total, we have 4 ohmic contacts, and we couple 2 such ohmic contacts together to get one terminal out. We call it a gate. And we have one drain and one source on both sides, right? So this was kind of the basic structure. And we also learned a few terms like voltage control device, which simply implies that here the output current, which is the basic property of any transistor that we are interested in, the output current will be a function of input voltage. We will see how it happens. We will see the operating principles and we'll understand that. And another thing is that we also learned that the current in this particular device is basically contributions of only the majority carrier. So we will see that later, that if we learn about bipolar junction transistors, BJTs, right? So these are the transistors usually we learn about it beforehand. So the name of those transistors are BJTs, bipolar junction transistors. So bipolar, the word means that there you have a contribution from both majority and minorities. But in these devices, JFETs, or the field effect transistor, so to say, you have unipolar devices where only the majority is contributing in the current. So the current constituted is by the majority carriers only. So these are kind of some terms that are very much compatible with 1 mark questions, right? What is field effect? What do you mean by an unipolar device? Give an example of a voltage control device, something like that. So we learned about the basic structure, and we ended up at this point where we learned very crudely the functionality of this device. And what we learned crudely is that we have 2 p-n junctions here, right? Here is a p-type, here is another p-type, and between I have an n-type. That makes us that gives us 2 p-n junctions. So if I bias these p-n junctions properly, and we discussed a lot about how to change the depletion regions width depending on the biasing conditions. We discussed that in the last class in detail. So now we know that if I have an appropriate reverse bias applied to a p-n junction, we can control the width of the depletion region. And we always remember that depletion, the word comes from depleted. That means no free charges. This is a no-no zone for any free charges. So that means if you have depletion regions, so these yellow regions are depletion regions. If you have depletion region somewhere, that cannot be a path for carriers. So here, the current that flows from source to drain, you can control its flow by applying our reverse bias voltage in those PN junctions by closing down this gate. Okay, so this is basically a principle like a tap where you have a source and a drain, and in between you have a valve that is these two PN junctions, or the or more specifically the depletion regions of these PN junctions, which you can control by applying a voltage voltage of biasing in these two junctions, and you can close down or open up this valve to get us flow from source to drain. So that is the working principle. At this point we ended up in the last class. So today we will focus in a more detail of how the circuit should look like, how the battery should be, what should be the proper biasing conditions for the working of a JFET. Okay, so going down to the working principle of JFET in a more quantitative way. So the first thing to understand about this is that the first point I want all of you to remember about the biasing of a JFET is biasing means adding some appropriate voltages between the terminals that you have so that the device that you have is in a proper working condition. So here, what do I mean by proper working condition? The first thing that is needed for functionality of JFET is that the carriers, the majority carriers of the channel, they flow from source to drain. Okay, so this is kind of a thing to remember, that the majority carriers of the channel should flow from source to drain. So the voltage that we apply between source to drain would be such that we call that VDS, V drain to source. Sometimes we also call that VDD, the voltage of the output circuit. So this VDS, the voltage that we have, the battery that we should attach in this circuit should be such that the majority carriers of the channel flow from source to drain. Accordingly, we will decide that which way the current flows, because you all know by now that in N-type we have majority carriers as electrons, in P-types we have majority carriers and holes, and because their signs are different, so the flow is one way, the current flow could be the other way depending upon it is electrons on holes. So if they are holes, the flow of current and the flow of carriers in the same direction. If they are electrons, the flow would be in the opposite direction, that you already know, right? So how do I attach this voltage source then? Let us see, it is an N-channel FET, okay? Then the carrier should be electrons, fine. I want the electrons to flow from source to drain. So I want the electrons to be attracted towards the drain terminal. So always remember that whatever flows in our tap picture are the majority carriers. Okay. So source to drain, the majority carrier should flow, electron should flow. That means the battery should go like this. The battery should be such that drain terminal is positively biased compared to the source terminal, so that the positive side of the battery attracts the electrons and the electron flows towards the drain. So I guess up to this point is clear that which way my VDS battery should be, right? VDS battery should attract the carriers towards drain. So if this is the scenario for the N-channel FET, then what is the direction of the conventional current? The conventional current here flows in the other direction. So this current, or this is the ID, that is the drain current of this circuit, okay? So drain current or the output current, this output current is nothing but this drain current. The circuit flowing in the source to drain circuit is called the output current of the circuit, and that will flow on the other direction just because the carriers here are electrons. Okay, so electrons are flowing from source to drain, conventional current is flowing the other way, that is the drain to source, because the sign of the electron is negative. I guess up to this is clear, right? So this is what we do. We change the voltage. Yeah.
And the orientation of VDS should not be opposite, because electrons are flowing from source to drain. So to attract the electrons from the source, the positive side should be towards the source. No?
Source to drain, right? So electron should move towards drain and repelled from source, right? Electrons should be attracted towards drain, right? So the positive side should be towards drain, because they should feel a positive attraction towards the drain terminal, right? Okay. So I guess it is clear, but that you always place your battery such that the carriers get attracted towards the drain terminal. So see what is the sign? The opposite sign should be connected to drain. So this is kind of the thumb rule of attaching your VDS. Okay. Once you attach your VDS, now you know which way the current is flowing, that also you know. So that is the second thing that we know by now. Now we are done with the output circuit. Now we have to worry about the input circuit, that is the gate source circuit. So gate source circuit, this part we have not attached any batteries yet, because this is the control, right? We know that here I will attach a battery such that this side, the N type side, and this side, the P type side, if we reverse bias it, we can control the width of the depletion region in this PN junction. So that is what we are going to do using the gate to source terminal. So if this part is clear, let us move on to the input circuit and think about that. So in case of the input circuit, the first thing that we will do, we will break this problem up into two parts. In the very first part, we will see something beautiful that is happening inside the JFET, even if I don't apply any voltage between gate to source. That is the first thing we will discuss when VGS, that is gate to source voltage, is 0. We'll put a 0 voltage between gate to source and see what is happening there. Then we will move on to higher voltages to answer the questions better, to understand the working principle better. Okay. So the first case that we consider, any doubts? Please mute your microphones, all of you. So the first case we consider is VGS equal to 0, right? So that means there should be no voltage between gate to source. Then what should I do? I should just simply connect them with a wire, okay? So I'm connecting gate and source with a wire and considering this as a ground, because this side of the battery is negative, right? So this is my ground, and VGS, both are short circuited. So no gate to source voltage is there. Now, if this is the scenario that I have not applied any voltage between gate to source, then what is the condition of depletion region now? Okay. If we understand this, the rest part becomes very easy. So I want you all to focus well in this particular section, what we are discussing right now. So if gate to source are short circuited, what is going on inside the depletion region of this PN junction? So I have two PN junctions, one here and one here,
the
right?
minority charge characters are flowing in the.
So just for now, ignore the minority carriers. That is the first thing that we have to do if we are learning about JFET. So don't think about minorities, because minorities do not contribute in the current flow in FETs. Okay, just think about the majorities. So I am short circuited this part. So no flow across these junctions. I am only considering flow in the drain to source circuit. So this is my ID. This is the current that is flowing in between source to drain. And if I am asking you that what is happening to the current, I am only worried about this current, ID, that is the drain current, that is flowing because of this battery. Okay. And I am trying to modulate the path of this current by applying a voltage perpendicular to it, that is the field effect. So what is happening at this point? What is the position of the depletion region at this point? And this is very, very important that we understand this. So let us consider this part, this point that I have given here, okay? And this point that I have plotted here on the gate. So what is the voltage difference between these 2 points? Is there any voltage difference between them? Or here and here, is there any voltage difference? Is there any voltage difference here? And so on. Let us consider these 3 points that I have just drawn on the source. So the first question to ask yourself should be, is the entire channel at same voltage? If I just connect the source and drain terminal together, does the entire channel and every part of this channel are at the same voltage? Because I can see that at drain we have VDS applied, right? But at source I have 0 volt applied. So that simply means that the PN junction that I have is not equivalently biased throughout the length of the junction. So what we can consider here is this. Consider that this entire channel that I have here, consider it as a resistance. Okay. And then now suppose this resistance is 6 ohms. Just suppose, for example. And now break down this 6 ohms in 3 2 ohm parts. Okay. So just consider that a resistance is connected here instead of the channel. Forget the JFET, forget everything. Just consider a battery and consider that a resistance is connected here of 6 ohm. So we know that V is equal to IR. That means the current flow through the resistance will be resultant into the voltage drop, right? Now, if I consider that the 6 ohm resistance is broken down in 3 or 6 smaller resistances, then after every resistance, you get a different amount of voltage drop. So this is a point that I want you all to think about a little bit. Ask me questions if you are having any doubts. So if I have a resistance of the channel, consider that as a channel resistance, right? I can imagine that that resistance is basically broken into several parts of smaller resistance. It's a distributed resistance throughout the channel. And that means that this voltage VDS is getting dropped throughout this channel, and different values have different amount of voltage drops present. So though one side of it is grounded, the other side is not at the same potential everywhere, because this voltage VDS consistently gets dropped at different points of the channel, making different points of the channel remaining at different voltages. Is this point clear or not? So I will stop here for a moment and see if you are comfortable with this thought of distributed channel resistance and voltage drop throughout the channel. Any doubts?
Ma'am, the voltage drop will not be uniform now.
No, at different points you will have different volts. Suppose if this battery is of 6 volts, so here you will have 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, like that, right? Because the same voltage will consistently get dropped throughout the channel. Okay, so that means that this side is at 0 or ground or whatever it is. This point it is at 1 volt. This point is supposedly at 2 volt. Here we have 3 volts. Here I have 4. Here I have 5. And at the drain terminal I have 6, because this is short circuited with the other side of the battery. Okay, so this is the basic concept, that this is something that if you understand this, the rest of the story becomes really easy. So try to just convince yourself that this voltage gets dropped throughout the channel, making different points of the channel remaining at different values of voltage. And that simply means that the PN junctions that we have, both sides, you have 2 PN junctions, they are not equivalently biased throughout its length. If we consider the entire length, the biasing is different. Here the biasing is least, here the biasing is maximum. Similar for the other voltage as well. So what we have is a picture like this. So here I have a very small biasing, a very small difference, very small resultant negative biasing applied in the PN junction. So the depletion region would be quite small. As you go on higher and higher down the channel towards the drain terminal, the biasing becomes more and more. And the width of the depletion region also becomes more. And it is maximum near the drain terminal. Same for the other one. Here, the depletion region would be small because the biasing is small. As you go on towards the drain, the biasing increases and the biasing is maximum at the drain terminal, making the depletion region having a shape like this, which is not very symmetric. So questions, doubts, if you have any. Clear? The idea is clear? Whatever we are discussing?
This, ma'am, this resistance gradient is inside the channel, right?
Inside the channel. The channel
JFET.
resistance, yes. The channel resistance, you consider the channel as a resistance, because as the current is flowing, it is facing some resistance, right? And the same voltage will get dropped throughout the channel. That means that different points in the channel will have different voltage. Right?
Is it linear?
Is it?
Linear.
No.
You can consider it to be linear up to certain point. Okay, so you can consider it to be linearly dropping. For conceptually understanding it, you can consider it as a linear for now. Okay, but the main point here to understand is the asymmetric shape of the depletion region. So are we clear about that? That we will have a shape like this. The depletion region, the yellow region, will not be symmetric, but it will be something like this, where the depletion region is very thin near the source terminal, but it is quite large in width near the drain terminal because of this constant drop of voltage throughout the channel. Okay, So if we understand this part clearly, then we can interpret that what is going to happen now. So if now I start changing the VDS voltage, okay, I start from a very low value, 0 value of the VDS voltage, and I consistently increase it and study that what is happening to the current. So the graph that we'll draw now, that is called the output characteristics of JFET. We'll discuss that in detail, but let us just for now consider that in the x-axis we are drawing VDS, in the y-axis I am plotting ID, the current flowing. Okay, so VDS is in the x-axis, y-axis is in ID. For now, VGS is equal to 0. We have not applied any voltage between gate to source yet. Now we start from a voltage which is 0 and change this voltage to higher and higher values. So what will happen? So when I start from 0, no voltage applied, so no attraction for the electrons, right? No current is flowing. So the graph starts from 0, 0. When there is no voltage applied, no attraction for the electrons, no force to pull the electrons towards the drain terminal, no current. So we start from 0, 0. Now, as I increase VDS, the force develops, the EMF is there, electron gets attracted towards the drain terminal, the electron will start flowing towards the drain terminal, and consistently a current ID will develop in the other direction. How the current will increase? Linearly. The current will go on increasing almost linearly like this. Just like the force is increasing and the current is increasing like that. Okay. But parallelly, something else is also happening. As you increase VDS, this voltage drop that we are talking about is also changing consistently, right? That means the width of the depletion region, though very small near source terminal, it is becoming quite large at the drain terminal. At the drain terminal, near the drain terminal, the PN junctions are getting biased higher and higher values of VDS. So at a certain point, what will happen? The depletion region will go on increasing and increasing, and after a certain value of VDS, these two depletion regions will be so close to each other that there will be barely a space left for the current to flow. Okay, so at that point, we will have this linear graph suddenly changing its slope in form of a knee, and then it will saturate. It cannot increase any further. Okay, so this is the kind of behavior that I will see. There are several points that to discuss, but just crudely, if I see that what is happening here is this: I increase VDS and the current increases first, but as the current increases, the voltage increases, the biasing that we have, effective biasing between the p-type and n-type near the drain terminal also increases. The negative biasing that we have in each of these PN junctions are increasing. And finally, these 2 points, these two depletion regions, they almost touch each other, leaving almost no space for the charge to flow anymore, resulting into a knee like this. Further beyond that point, the current cannot increase anymore and it saturates. Okay, so this is the first curve among the set of curves that we are going to draw in the output characteristics. So this point where these two voltages, these two depletion region touch each other, this value of the voltage that we have here, this is called pinch off voltage. So the value of the voltage in the VDS axis, this one, okay, it is denoted by VP, and whenever you buy a JFET, this value is specified when you buy a JFET. Okay, so this is called pinch off voltage. Pinch off voltage. This is the voltage at which the channel closes. This is the voltage at which the channel closes. It is called the pinch off voltage. So pinch, you understand, you can know the word, like from the recipes we know a pinch of salt we say, right? So pinch is basically when your two fingers are just touching with each other. That is called a pinch. So at this point, these two depletion region, they just merely touch each other, leaving barely a space between, so that the current can not increase any further. Okay, so that is how you get a pinch off in the output characteristics. So this is kind of a more clean version of whatever I was trying to draw there. The current at which it saturates for VGS equal to 0 is called IDSS. IDSS. I, drain to source short circuited. This last S is for short circuited because we have short circuited gate and source. Okay, so this is the maximum current that is flowing in your circuit. We will see that for further different values of VGS, the current cannot go beyond that. So this is also a specific constant associated with a JFET. Okay, so when you buy a JFET, these two values come specified. One is the maximum drain current. This is called the maximum drain current, IDSS. I, drain to source short circuited gate. The gate and source terminal are short circuited. So this last S is for that. And the pinch off voltage, VP. Okay, this is called pinch off. So is this clear? Is the idea of the first output characteristics for VGS equal to 0 clear? Any doubts?
Ma'am, I have a question, ma'am.
Yeah.
Ma'am, when the two depletion region merges, then the current should be 0, na? Because there
very
are no
good, very good. I was just expecting this question.
Yeah,
Very good. So this is kind of the question that comes to our mind, right? That why does not it fall down to 0 like this? Because once the depletion region closes, the current should fall down, right? That very good question. This is something the normal notion will tell you. So let me just explain this, because what happens here is this. So just consider this scenario, okay? I am increasing VDS, the current was increasing further, and the depletion regions were also growing, and they have just touched, okay? So let us consider your notion. As soon as they touch, the current will stop. As soon as the current will stop, what will happen? As soon as the current will stop, the entire voltage drop that we are getting throughout the channel, that will be lost, because there is no current flowing in the circuit anymore, right? The moment the current stops, the reason for which the depletion regions were getting formed, that gets out of the picture. So this is a very good point to think about. What happens is, immediately after the current stops, the voltage drop goes off, and the depletion regions again move away from each other, right? Because there is no voltage drop anymore. So they will go away, and again the voltage, as they have opened, again the current will start flowing, and again the voltage drop will be created. So it is like they are vibrating very fast, just opening and closing the gate very fast, but they cannot stop the current. Is the picture clear to you? Just
Yes,
think
ma'am.
about it. Okay, so it is because the reason for the depletion regions to get formed is this VDS only. And if you don't have any current in the circuit, you don't have that entire picture of variable channel resistance and voltage drop, different voltage drops at different points, which actually makes this asymmetric picture of the depletion region. So it is happening like this pinch is opening and closing very fast. The gate is opening and closing very fast, maintaining a constant current. Okay, so the current cannot increase any further, but it also does not drop down to 0. It becomes constant, it remains constant. Okay, so that's a very good question, and that's a very that actually develops a very good understanding about how the JFET works. Okay, so I guess the idea of this entire thing of how this JFET characteristics, first curve of JFET characteristics we can draw, is clear to all of you. Let us just quickly, we have just 5 minutes left. Let us just quickly think about the other voltages. Okay, so other voltages would be when you have make more and more negative biasing by applying some voltage in the circuit. So which way the battery should be if I want to reverse bias the gate to source junction now?
Just opposite.
Gate side is P, right? Gate side is P type. I want to apply a reverse bias. That means the gate terminal should be on the negative side of the battery. Clear? Okay. So I want to apply some control voltage, some reverse bias voltage between gate to source now as control parameter. I want to make VGS something else, something other than 0. Okay. So if I want to apply more and more negative reverse bias through the junction, then I have to apply a battery. I have to add a battery like this. As soon as I add a battery like this, the entire picture remains the same. The only thing changes is that when you have VDS equal to 0, still there is a substantial amount of depletion region because of this battery present there. So that actually generates a curve whose slope is a little bit less than this one. And again, it saturates like this. Okay. So you have another curve for different values of VGS like this. So for suppose this is VGS equal to -1. Okay. So this is equal to -1, this is equal to -2, and so on. So
Hello, ma'am.
Ma'am, you are not audible.
how far have you heard? Hello?
Up to
Am I audible?
VGS to
No,
the
just
-2.
starting.
Okay. So VGS equal to 0 part we have discussed, right? VGS is equal to other values like other negative values. We will start our discussion from there in the next class. The only thing that I want to mention here is that if I want to apply a negative bias between the PN junction, using the gate to source terminal now, I have to attach my battery like this, where the P-type side will be connected with the negative side of the battery and the N-type side will be connected with the positive side of the battery. And the different graphs that I will get for different values of VGS will just have different slopes to start with. Okay, so I will start from this point as we have missed some of the discussion because of some problem in internet maybe. So let us stop here for a moment, think about whatever we have discussed, pinch off and VGS equal to 0 condition. We'll discuss for other VGSs in the next class. Okay, any doubts you can ask me now.
Ma'am, V pinch will increase now, ma'am. In the last, go to the last slide which we were talking
This
right
one,
now.
this one.
I can't see. I think next year this one, ma'am.
Which one?
Ma'am, V pinch should now increasing for -1, -2 now.
Now that you have to think about, that it will increase or decrease. Okay, we will discuss this in detail, that V pinch will increase or decrease. It's actually going to decrease, but why it is going to decrease, that you have to think about, that we will discuss in the next class. Okay. And there are several questions like this, that what will happen if I reverse the gate to source voltage to positive? What happens then? Why V pinch off will decrease if I have other values of VGS? Okay. So these questions we will address in the next class, and we will strengthen our understanding about the output characteristics, and we'll also talk about another characteristics which is called transfer characteristics of JFET. So these things we will talk about in the next class. Okay.
Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
No other questions. Okay. No further questions,
Thank
right?
you.
Okay.
No, ma'am.
Okay.
Thank you, ma'am.
Then so this week
Thank you,
the
ma'am.
Wednesday's class also I am going to take. Okay. So Wednesday also I will take the class. We will meet on Wednesday then. Okay.
Okay.
Sure.
Yeah, ma'am.
Okay. Chalo. See you guys later.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Ma'am, can you please
Thank
send the
you,
PPT?
ma'am.
Huh? Tell me.
Ma'am,